Good morning, everyone. I am recording this from Jinan in Shandong province in China, where I had to come for a short work-related visit. I'm grateful for this opportunity to share with you what I see as possibilities in the chemical engineering area, particularly for innovations in chemical manufacturing. It's an area that's very dear to me, using advanced computational models. And I would like to make the case for my excitement. There are a lot of other reasons to be excited to be a chemical engineer these days. If there is time in the Q&A, if I'm able to join live, I will be happy to answer those questions. So I recently retired from Louisiana State University in the US, and I retired earlier from Alberta 15 years ago in Canada. Currently, I'm a visiting professor at IIT Indore, and I'm also a chief scientist at the Shandong Academy of Sciences, and that's why I am in China right now. Let me see my... this talk is based on an article that we wrote in ACS Engineering AU called Perspectives on Manufacturing Innovations by the same title. And I co-authored it with some of my colleagues, Professor J.B. Joshi. Many of you may know him very well. He's a well-known chemical engineer in India. And also my colleague at the LSU, Dr. Valsaraj, and Professor Nigam from IIT Delhi. He's also a retired professor. All four of us are retired in some sense. So what you see on the left-hand side is what a chemical engineer does. Many of you are chemical engineers, so it's probably very familiar to you. We essentially capture or harvest materials and energy. The source of these can be a wide variety, from biomaterials, from fossil fuels, from energy, from nuclear, from solar, etc. And we use these to using conversion technologies. That's where I'm going to focus on. What are the opportunities for innovations in the conversion technologies to produce products for humanity? And we want to do this in a sustainable manner. There are lots of opportunities for innovation in terms of new chemicals, etc. But there are some challenges in terms of innovating the manufacturing processes, and that's what I want to focus on. This is the cover page for that article, and the cover page was actually drawn a decade ago by my daughter when she was in the 8th grade, and it captures beautifully how evolution has created very complex life forms. And we still don't fully understand it, but we are on the verge of making some significant breakthroughs. So, for example, natural systems, what are they and how did they evolve and what can we learn from them is going to be a source of inspiration for us. You see that basic chemicals combine together to produce more complex organic and inorganic chemicals and biochemicals, and then they are encoding that information and then giving rise to higher and higher life forms. And of course, we need the source of energy, and you have the ocean, etc. So it captures by an 8th grade student the idea, and she submitted this for one of the ACS local chapter competitions. So there is a lot that we can learn from nature, but engineered systems are the ones that we chemical engineers build to extract the specific chemicals and pharmaceuticals and fertilizers, energy, etc. that we need. So the outline of the talk is going to be a little bit on what is the innovation and invention, what's the difference, and what role has computers played in this innovation, and what are the challenges in rapid innovation in chemical manufacturing processes. And I'm going to talk about what I call M to the power 5 framework to accelerate the pace of innovation in chemical engineering. What I mean by that is multi-scale, multi-physics, multi-phase mathematical models. And using computer solutions of these mathematical models, how can we improve the design of multi-phase mixtures, solid liquid, gas liquid, liquid solid systems, from molecular scale to mesoscale to the macro scale, plant level scale. So that's where you have multi-scale and multi-physics, because many different processes occur at the same time in a multi-phase mixture, and how can mathematical models help us do that. Once I said, it's not going to be a talk dwelling into mathematics or computer programming. It's going to be general conceptual one, and I will give you a few examples and make some concluding remarks. So this is a slide that I borrowed from a president of ASCHE some years ago, and it basically talks about the evolution over 2,000 years. 2,000 years ago, for example, 98% of the human population were involved in producing the food, agricultural industry, right? But what has happened over the years as time evolved is manufacturing has increased, and so more and more people are engaged in manufacturing, particularly in the last 400 years or so, or since the Industrial Revolution. But even before that, manufacturing was beginning to play an increasingly important role. Currently, only 2% of the population is engaged in agriculture, and they are able to produce the food needed for 7-8 billion people. That's a remarkable improvement in innovation in agriculture, right? And chemical engineers have played a big role in doing that as well. And in the last few years, 2 decades, I should say, the employment in the manufacturing has also gone down. And the reason for that is that automation has stepped in. And these are the actual data about the percentage of people engaged in manufacturing that have gone down from 30% to 16%. In various countries, the trend is the same. And of course, right now, AI is stepping in a big way, and there is a lot of concern that many more people may be unemployed. But what I would like to do is project a positive view that if when you had 98% reduced to 2%, what did the remaining people do? They did not just get out of job and got bored. They were more creative. They were creating in other things. That's how the manufacturing industry evolved. So from manufacturing, we are going into an IT and AI-based industry, and more people will be engaged in that. So I don't think there is a cause for alarm in the long run. In the short run, the people will be facing adjustment problems, and society has to have mechanisms to take care of people that are displaced by these rapidly evolving technologies. And this is another slide that I picked up from one of the TED Talks, and it plots over a period of time without any scale, actually, increase in productivity. But there are 2 significant points. One is when we learn to overcome our muscle power. Here you see the 2 kids running a mill. Okay, and when we learned how to overcome that with steam engine and muscle power with machine power, the Industrial Revolution happened. That increased the productivity somewhat. Okay, but what we are facing now is a machine learning revolution or AI revolution, where our brain power limitations are being overcome with the help of machines. Okay, so it's expected that the productivity will increase exponentially, and many people are predicting this. Ray Kurzweil is one book that you can, the book Singularity is Near, is one that you can read to get an idea of how he projects the evolution in productivity to increase. This is illustrating the machine learning revolution itself. Okay, so think of this y equal to mx. This is an equation that all of us can easily wrap our minds around, but it illustrates the point beautifully. It is a talk by Blaise from Google, in fact. And think of this as a model that relates 3 symbols, y, m, and x. Okay, so I want to illustrate this using this idea: what is learning, what is predicting, and what is creating? And how does this occur in both physics-based models and in machine learning models? So here is the idea of learning or training. It's very similar to how children learn. Computers are beginning to do the same thing. So we teach by showing millions of pictures and labeling those to various words. Okay, it's a flower, it's a face, it's a cloud, etc. So we have a database on Y and we have a database on X, and we are trying to map Y to X, and the learning process is discovering what is M. That is a curve fitting, some people might call it, right? So what is M? M would be a huge matrix, X would be a huge vector. In fact, this model will be replaced by transformer models these days in large language models, etc. And in engineering, it will be replaced by very complicated physics-based models. Okay, so this is an example of what that Y, M, and X look like. Okay, so this is a picture, a digitized picture put through a neural network where the weights are adjusted and mapped into bird. And we trained this with millions of pictures, and we have been very successful in doing that, right? Once we have learned that, once we know what M is, what is the prediction problem? The prediction problem is then to a child that has seen hundreds of these pictures, for example, even at the age of 1 or 2, you show the picture then and ask, what is this picture of? The child will be able to recall. It's a flower, it's a car, whatever that is. So here Y is given, M is learned in the first step, and it is able to predict what the X is. The unknown changes to X now. So in science and engineering also, we have similar problem of building a model and predicting the performance behavior from that model. The last step is the creation problem. Creativity. Can the same model be used to create new designs, for example? So to pursue this example, once I have learned M, if I give a child a crayon and say, draw me a picture of a bird, the child will do a good job. Okay, may not be the best artist, but it's understanding of what a bird is. The question then is, can a computer do that? Can computer create what that Y is? And 10 years ago, this was the picture that was created by a Google computer. When you say bird, it created this. Today, it can do amazing things. I'm sure all of you have heard of or played with DALL-E, the image creation program. And it can create pictures of things that nobody has seen, that didn't exist. As long as you can give the right prompt, it can create those. So those are the 3 problems that we have to deal with. Now, coming to the chemical industry, it's a huge industry in the US and in India too. And innovations occur in terms of creating new chemicals at a phenomenal rate. By the time I finish the sentence, one new chemical would have been synthesized somewhere in the world. It's apparently 2.6 seconds. Every 2.6 seconds, a new chemical is synthesized. And in terms of documenting it, Chemical Abstract Service has documented 182 million known chemicals. Okay, and it took 33 years to get the first 10 million chemicals registered, documented, cataloged, and it took only 9 months to get the last 10 million chemicals into the database. Again, this shows how rapidly the innovations are taking place in terms of even documenting, just writing it down. How many different chemicals do we know? Okay, so there is a phenomenal increase in the rate of innovation in these chemicals. Not all of them are useful for every purpose, but there are clearly 10,000, 15,000 chemicals that are produced in various quantities. And what about other industries? Okay, so here I'm talking about automotive, aerospace, and computers. Okay, so invention is something that you create that doesn't exist before. Innovation is something that you successively improve in a very sustained manner. Incremental every year, 2% in efficiency, 3% in engine efficiency, 5% in drag reduction, etc. When you do that, you make phenomenal improvement from a Model T in 1900s to a modern Porsche, which is 1,000,000 times much better in terms of its performance. Similarly, from a Wright brothers to a modern Dreamliner. And this, I don't know whether any of you know this, this is the ENIAC computer, the first computer, room full of diodes. Okay, and they were doing about 10 flops or 100 flops or something like that, floating point operations per second. And now everybody holds a phone in their hand, and it is 1,000,000 times faster than the ENIAC computer and 1,000,000 times smaller. Okay, so that shows the phenomenal growth in improvement in technology caused by innovation. If you ask the question, what is it in the chemical industry? This is a chemical distillation column in the 1940s, and it is the one in 2016. It's a bit more glittery because it hasn't rested. But if you look at the inside, there has not been significant innovation. Some people may argue with that. I'm willing to argue with them. But the question that I'm asking myself is, why is there not a rapid innovation cycle in chemical process design? Okay, we are creating chemicals in a large number of quantities at a very rapid rate, but process innovation hasn't taken place. This is an example of a distillation column, okay? A single tray. You can see the size of it, 20 feet probably in diameter, okay? And they are used in a lot of gas liquid separations. And typically the liquid comes down, flows across and over the weir, and the vapor bubbles through these, and the vapor and liquid are contacted, they exchange the species, and then they separate, disengage, and go their way, right? And here is an example of, this is produced by a company called Fractionation Research Incorporated in the US, and it shows how complex the flow phenomena is in the interior, okay? I guess I should let them play. I cannot play all at the same time. So what you see here is on the left-hand side, it's called a weeping zone. Essentially, as you go from the left to right, the vapor flow rate going upwards is increased. So if the vapor flow rate is very low, then the liquid from the tray above drips. And this is called the weeping phenomena. So instead of separating, we are mixing, okay? The ideal place is the froth regime, where there is a good vigorous mixing of the vapor and the liquid, but the vapor zone disengages and goes up, and the liquid zone goes down after they have exchanged their equilibrium position. Now, the third one is the vapor rate is so high that the vapor is actually the bubbles are entrained in the vapor that is going up. And again, you result in mixing. And the secret to predicting this flow behavior is contained in the Newton's law of equations of motion for the fluid. This is called Navier-Stokes equation, and we know the equations fully well, but we cannot solve them because these are highly nonlinear. And with the computers, computational fluid mechanics, we are able to solve in a limited sense. There are still enormous amount of challenges in terms of solving these equations to predict the performance. So it takes 20 years to design a particular process, whether it's a distillation column or the catalytic cracking unit, etc. It takes 20 years. Why? Because we have to develop them through a pilot scale testing at various scales. And I will tell you why that is so in the upcoming slides. This is a picture from the National Energy Technology Lab by the Department of Energy, and it shows how complex a solid liquid system is. The previous one I showed you liquid vapor, but you have to watch this. They continuously zoom in to see how complicated the phenomena is. This is for fluidization, another commonly used process equipment design. So there are particles there, and the gas or a liquid is flown up, and they just fluidize the entire particles. That is essentially the particles and the fluid becomes like an effective fluid in a sense. And you will see from high-speed camera with 10,000 frames or something, they are able to predict what the velocity of each particle is from the measurement. Okay, they calculate from the measurement, they are able to calculate. The question, of course, is can we use equations and predict them without using these experiments? This is essentially showing the velocity vectors of this combined mixture of particles. This is a riser in a catalytic cracking unit. And what you see here is a cluster of particles that are descending near the wall, but the particles in the middle and everywhere on the average, they're moving up because the upward flowing fluid carries the particles. But here you see the cluster of particles coming down. So it's a very complicated behavior. And this is now at 40x. And what they do is they take these data and put it up as a challenge for modelers to see whether you can predict the behavior of such complicated systems. And that's where the challenge is in a rapid innovation cycle. And I will point out in a little bit more detail after this video finishes. So now they're zooming back to show how complicated that particular process is. And what are the equations governing them? They're going to give you a brief idea, but I don't want to spend too much time on the models because they are indeed very complicated partial differential equations. So there they are. This is available in YouTube. If anybody wants to go in detail, you can go and view the videos in greater detail. This is courtesy of Professor J.B. Joshi. So he had this nice slide that illustrates the multi-phase nature of process units in chemical engineering: bubble column, a fluidized bed that I just showed you, agitated slurry contactor, and a wiped film contactor, structured packing, etc. And every one of them, multi-phase flow is a common feature. Okay, solid, liquid, bubble, liquid, liquid, immiscible systems. All of them are, there are about 400 such equipment. How do we design it? Okay, so that's a good question. So we do experiments in the lab scale and measure what the performance is and correlate them in dimensionless form. This is an example of heat transfer in various equipment: pipe flow, bubble column, stirred vessel, fluidized bed, etc. There is such a correlation for mass transfer, fluid mechanics, drag coefficients, etc. By putting them in dimensionless form, we expect somehow magically that they will be valid on all scales. And so by doing experiments in a 2-inch diameter pipe, I can use that to design a 30-inch diameter pipe. It doesn't work that way. And we will have to understand why that is so. Right. And here is a scatter in the holdup, the volume fraction of the bubbles and the bubble column by 15 different people. This is again courtesy of Professor J.B. Joshi. And what he shows is that the scatter, phenomenal scatter in the data of predicting what the gas holdup is on the average sense in the equipment. And if you take each one of those correlations, they have done the experiment and they have proposed an algebraic equation as a correlation, and they will predict very well. But if you take that correlation and apply in the domain of somebody else's experimental data, the scatter just goes haywire everywhere. For a database modeler, this is good news because they have rich variety of data and machine learning models can use that. And that's where there are certain opportunities for taking these data and organize them in a way that will allow us to synthesize and improve our predictive capability. We have seen that in the protein folding problem. We have seen that in crystal structure prediction problem by Google DeepMind. But in chemical process engineering, we are not very systematic in terms of documenting these data yet. This is an important slide that underscores what the problem is. When I do an experiment on a small scale, okay, suppose I have particles in a fluidized bed, and I have a distributor here, and the particles are going up, and it creates a circulation, as we saw. The fluid circulation is on a much larger scale than the particle scale, but the mixing that occurs is limited by the diameter of the equipment. Okay, so the diameter of the equipment filters out any possible larger size circulations. So we measure the data from this. We correlate it in terms of Nusselt number, and then we go into predicting the next pilot scale size. But what happens is the diameter is large, so the larger circulations form. The particle size or the dispersed phase size remains the same, right? So we need to capture exactly what are the transfer processes, momentum, heat, and mass transfer processes or reaction processes on the dispersed phase scale, because they will remain the same on all scales, but they drive a circulation because of the density difference between a cluster of particles or a cluster of bubbles. We see that they form larger circulations. If you take it to the next scale, the circulations are even larger. So if you measure the Nusselt number here and try to predict the performance here, it's going to be miserably failing. And that's why we need to do some intermediate scales to continuously improve on the correlations. And question is, can we do better by using either machine learning models or by using fundamental principles of fluid mechanics, heat transfer? And here I'm going to identify, I have identified a few key parameters that needs to be measured on the dispersed phase scale. And it is possible. That's a separate topic in greater detail on the mathematics behind it. But everything that I've shown here in red is a parameter that doesn't remain scale invariant as you scale up. So here is an example that illustrates it. It's an experiment that we did in our lab. The idea is to mix. So we put a dye into a tank of water, and the energy supply is from a moving piston at the bottom. So you see the complex vortices that form, and those are the ones that cause the dye to mix. It's going to take a certain while, and we have a paper on this that studied the mixing phenomenon. Here is another example of bubbles being dispersed in a stir tank, and this is the kind of nature-inspired mixing that I'm talking about. Here there are two channels that are continuously divided and divided. These are called fractals, and they don't mix anywhere near until they come to the final stage where the two streams are mixed together. So you see at the outlet, everything is homogeneous. Okay, perfect. Human body has such fractal natures for carrying out complicated mass transfer. For example, lung, where the air passage is there and the blood vessels come, and there is a membrane across which they transfer oxygen and carbon dioxide interchange, and then they carry on doing their job. So this is a fractal thing that we designed for a distillation column, and this is fractal in nature. Right, so this is a fractal in nature for the lung. On the left side, you see the air passage. On the right side, you see the veins, and they coexist in both the sides. And they do a wonderful job of selective transfer of carbon dioxide from the blood to the air, and selective transfer of oxygen from the air to the bloodstreams. And that's a phenomenal thing. Now, this is a very dense slide, and for a outreach talk, this is probably too much. But what I want to highlight here is we need to understand how molecules interact. After all, chemical engineers are dealing with chemicals, which are molecules. And we want to, what do we do? Typically, we do three things, right? If the things are mixed, we want to separate them, distillation, absorption, etc. If things are separated, we want to mix them. Like in a reactor, we want to bring two reactants together, mix them, and then react them. So the third one is a conversion. So separation, mixing, and conversion are the three things that we do, right? So we need to understand from the molecular level how these things occur, because they occur typically in a fluid, liquid, gas, and a solid, as a catalyst or as just a support medium. And so the scale at the top is the Aspen scale or the Planck scale. And to go through this process, we do it experimentally by doing various pilot scale experiment. The question is, can I build what I call a digital twin for the entire process? Okay, so that every level you study, you are taking some input and predicting some output. And that becomes the input for the next scale, and that predicts some output. And this goes on all the way to the Aspen level type of a model. And in parallel, these days, we are able to use the data-driven model, right? And our goal to look at innovation is to look at the mesoscale model and come up with alternate designs to simulate in silico what are the best design methods before we build a pilot scale. We can do that if we can trust all the heat transfer coefficients, mass transfer coefficients that are predicted from fundamental simulation results. I'll give you two examples. One is a polyethylene reactor that we did as a retrofit to an existing plant, and a new design of a fractal distributor and how we went about that. And so there is a design optimization cycle that builds on the mesoscale modeling, predicts various designs, and optimizes that, and then cycles through that. And of course, the data all the way coming from pilot scale, whether it's viscosity or mass transfer coefficient or the volume fraction, etc., get into these models at various levels. And the model themselves can recycle those, okay, in the data prediction. So it's a very complicated web of a network between various models that we have laid out, what we call enabling process innovation through computation. So how does computers help innovate? Okay, so so this is the data, rich data that we can use to build the data-enabled models. So we should keep in mind one of the very famous quotation by George Box, a statistician, that all models are wrong, some models are useful. So any model that you consider will have certain limitations, and we need to be aware of that. So let me start with the first example of a loop reactor. And one of my former students, Mr. Ratnesh Tiwari, contacted me after he graduated. I came to LSU. I was teaching in Abu Dhabi for a couple of years. And he phoned me and said, Kumar, we have this problem in a plant for a polyolefin reactor, and we wonder whether you can help. And so they came to Baton Rouge, and we brainstormed for 3 days, and then we ended up with the project. The problem is the following. What you see here is slurry density or the pressure in the loop reactor that's wildly fluctuating. When this happens, it fatigues the pump, the failure occurs, and also they cannot push the production to a higher capacity. So the question is, can we somehow get rid of these wild fluctuations, identify what causes the fluctuations, and how can we get rid of it? Now, what is the reactor? The reactor is a closed loop. It's called a loop reactor, and there is an internal pump. And the pump circulates the reactants. It could be ethylene or propylene, and there are some catalysts seeded nano-sized particles. And so the reaction, the polymerization takes place on these nanoparticles, and they grow in size to about 3 millimeters size or so. And incentives to either grow the size to be a larger size or to grow more number of particles so that your production capacity increases in an existing design. So what we thought was that maybe there is a cluster of particles. We have seen this in other areas, right? Cluster of particles. And when the pump is pushing the cluster of particles, it has to do work against gravity. But once it goes to the other side, when it descends, the pump has to do less. So maybe there is some sort of a load. And when the cluster hits the pump, for example, that can also cause. So we set up a proof of concept simulation. And what you see here is the pressure. Maybe I should go back one step. So you watch the pressure, the power consumption, and this is a single loop, but the real reactor is much, much bigger. There are 8 loops perhaps, and it's 50 meters tall, and it's half a meter in diameter. But this was done with a 1-inch tube in a simulation to showcase. And what you will see is that the pressure goes up, the power goes up, but then when it goes to the other side, they will go down. Okay. And so we said we understand what is causing it. So let's set up a full-scale simulation. So these are some of the details of the full-scale simulation. And the way that we went about is, we said, okay, let's take a simple bend and put uniform particles here and see what happens to the particles as go through the bend, because centrifugal force should cause the particles to segregate. That is one of the mechanisms, right? And we use something called a discrete element modeling or discrete particle modeling to do this simulation, just a bend alone. And we did see the particles are all going on the other side. So this is where we sample it to see what happens. So we have an idea of what causes it. Then the question, this is the actual 8 loop that you see, and it's fairly large. It's a real scale problem that we set up in the simulation, and the pump is somewhere here. Okay, and as it goes through every bend, there is a possibility for segregation, right? And that is what you see here. What you see is the color is proportional to the solid volume fraction. So the red means that there are probably 30%, 40% solid volume fraction, and the blue means there are no solids there or close to 0 solids as it comes out of the bend. Okay, and our goal is then to devise something so that it will swirl it, it will mix it up so that by the time it goes to the next bend, it's uniformly distributed. So we said, okay, let's come up with a design criteria. That is, how uniform is the concentration? Okay, and then let's come up with a design alternative, which is we will build inside, this is done in simulation, right? Build inside a set of vanes, and we'll adjust the number of vanes, the size of the vanes, the depth of the vanes, etc., and see how successful the vane is in terms of introducing a swirl. And you're going to see the animation of it. So you can see that as it goes up, this is an image as it goes up the pipe, and the centrifugal force induced by 6 vanes is so large that the particles are thrown outside and there is no particle in the center. We said, okay, that's not a good design. So let's go and reduce the number of vanes to 4. We want uniform concentration. This time it's rotating in the opposite direction because we need to be cognizant of how the bend comes about so that we can direct its motion. So this is better because the variability is 6.5%. Here it's 5.1% variability in the concentration across. Finally, we said we'll just put two small veins and see how that does work. And we are able to reduce to 1.2% variation in the cross section. So essentially, it's fairly uniform across the cross section by the time it reaches the midpoint of the pipe as it goes up. So that was our design innovation, a very simple retrofit to an existing problem that was achieved using a CFD, multi-phase CFD modeling. Okay, and this is the slurry density profile after we put these veins after every one of those bends, and we are able to reduce it significantly. What does it mean? It means they have the option now of either increasing the concentration of the particles or increasing the size of the particles so that they produce more pounds for the same amount of energy consumed, etc. So even if they produce 5% more, it literally means millions of dollars. And they spent peanuts in terms of supporting this work. It demonstrated for them that these kind of models are indeed helpful. We then continued. They came back to us and said, okay, let's do other variations as well. So what would happen if I put a connection between two sections, or what would happen, where to draw the products in the best location, what should be the design of the product withdrawal port. It's a continuous operation. So there are lots of opportunities for posing questions in existing plants, and anybody that is interested in exploring, we can build a similar group at IIT Indore to help, and that way you are also training the future students in using these tools. The next example I'm going to give, I think I'm just looking at the clock. I think I overshot it, but let me just conclude it with this example. This is a new design, okay? And the problem that we are addressing, these are fractals. I think you already know what fractals are. Fractals are geometric entities. It's a mathematical thing that was invented by Benoit Mandelbrot. And it's essentially a self-similar pattern that keeps scale invariant. That is, as you zoom in, you will see the same pattern repeating forever as a mathematical object. In physical systems, you do see that too. Like as I said, in the lung, and this is a broccoli, but there are limits to the scale over which the scale invariance will exist over a certain order of magnitude of scales. And the problem that we were interested in is let me see whether, oh, these are other examples of fractals in nature. But the problem that we are interested in is, this is a standard distributor called the Koch glitch distributor that is used in packed column for distributing liquids, whether it's a distillation column, absorption column, or a solvent being distributed. And the design is such that you have one input here, and there is a manifold there, and there are many outputs, okay? And the liquid will drip through these. And there are empirical design criteria on how many drip points you should have per square feet of the packing, etc. The problem with this one is the flow rate is not uniform from each one of these drips. This point is the closest to the manifold, so it will have the highest pressure, so it will put out liquid at a very fast rate. And this one is quite far, or this one is quite far. So the flow rate will not be uniform for each one of the dipping points unless you maintain the pressure so high here that the pressure drop is a small percentage of the high pressure. That means you're putting a lot of energy and you're wasting all the energy because all of them are dissipated eventually. So the question is, can we design a geometry where the pressure drop is the same and the flow rate is as uniform? So here you have one inlet. It is split into two, and it's split into two here, and it's split into two again, and it's split into two again. So finally, if you look at the distance between the inlet and the outlet that is closest to it, and the inlet and the outlet that is farthest to it, and then trace the path, you will find it's exactly the same distance. You come here, go this way, come back, go there, go there, go there, and that way. So if you go the other way, it's going to be exactly the same. So you made the resistance length to be the same. Okay, and so one would expect that this would produce a much more uniform flow rate, and it doesn't happen. Then we can ask why that is. Okay, in silico, in a computer. Okay, so this was a PhD thesis by one of my students. So what he did was he took a plate, and a filter press kind of a design. And he will have, the next one I will show it better. He'll have one inlet, and that is split into four. And these four outlets are matched on the other side at the center of these four, on the other side of B. And that comes this side, and each one is split into four. Okay, and from the tip of each one, you will have now 16 inlets on the backside of C, and that will give you 64 and 256, etc. You can scale it up very quickly, and these things can be designed in AutoCAD and sent out for fabrication. And so you take one input and then you split it into uniform output from this side. And this is the place where your absorbent or whatever that you want to use in the center. On the other side, you have the inverse of it. So it collects it in the same way from 256 to 64 to 16 back. So you have ABC is the same as mirror image of EFG. Okay, and the student came up with some other innovations to address some of the problems that we faced in the simulation. We learned about all these things in the simulation. That was to provide a conical expansion. And I will show you the design. So here is an animation that he made in SolidWorks, I think. So it shows how these things are assembled. Okay, you can see it from both sides. And he built then an experimental setup to see what is the residence time distribution. What is the goal in here? If a molecule that enters has the same residence time, whatever path it takes, then you should have a spike for residence time. But if they have different paths, they stay different longer times, then you will have a broader distribution. The moment you have a broader distribution, the experience of each molecule is different, and that's what gives rise to heterogeneity in the product quality, etc. So he built this equipment and actually measured with only 16 outlets, maybe only with two plates, right? And then he did it with 3 plates and 4 plates, and he could see that the narrowing of the residence time distribution. He just used a salt solution and used conductivity probe on the other side. And there are dispersions occurring through the tubing, etc. But you could see that in general, the distribution becomes much more uniform and narrow. This is the simulation of how the fluid, from a simulation, visualization, how it splits. And watch what happens. As it comes out here, the innovation was to put a cone so that it expands gradually, and then it will come out as a very uniform front. So whatever happens, absorption or whatever that happens, reaction in this packed bed, all the molecules are going to have the same residence time. So the product quality as it comes out on the other side is going to be very uniform. That's the basic idea. But there is always a but. He took the predicted flow rate, oops, let me go back there, and he found from each one of these holes, there is a variability in the flow rate, about 7% variability for his initial design. And he asked the question, this is a curious mind of a smart graduate student that enables him to ask questions and find the answers from simulation alone. So he asked the question, why is this variation? And his design was that it comes here, turns around, and then splits, and then splits. And every time it splits, turns around, there is a vortex that is formed on both sides. And in this here, there is only one. So by the time it reaches to the next level, already there is an asymmetry in the distribution. Small though, but it is there, right? And so his thought was, then how can I mitigate this problem? So here you can see there is more liquid going this side than here, because the vortex there offers a resistance to one side of it. The liquid flows through the other side, right? So his clever idea was, okay, now I'm going to change the aspect ratio of this distributor as it comes. And you can, listening to it, you can come up with a million other ideas. You should then go into the computer simulation and explore them. This was one idea to illustrate it. So what happens if I change the aspect ratio from a wide like this to a narrow one? And he systematically studied. He did hundreds of simulations. And what he found was that there is a region for aspect ratio and flow rate where the coefficient of variation is less than 1%. That's a good design. Whereas at the other extreme, it is quite high, 30%, for example, right? And what causes it? He basically looked at the profile. So this is a wide channel, and you have a large vortex here, and the separation is non-uniform, this will give rise to high coefficient of variation in the flow rate. Whereas if you have a narrow one, it still produces, when you turn around, a small vortex, but it has enough length so by the time it reaches the next splitting point, it becomes more or less uniform. So this produces a lower variation in the design. Now, you can say, okay, how about if I make this smooth, or how about if I make it come from the top? Those are the design innovations one can explore in silico on a computer before you actually go and fabricate it. That's the point I want to make. And then he went on to design a number of other fractal distributors for other geometry, circular geometry, etc. This is supposed to be an animation that he did, experimental data that he did for a bubble column that we were using, but this animation is not working here. So I will skip this part. This is a novel static mixer design based on the idea of something called coiled flow inverter that Professor Nigam had done a lot of work. But listening to the seminar by Professor Nigam at LSU, my student came up with this idea of, what about if I make a tube that is completely coiled like this so that the curvature is continuously changing and it produces better mixing. And so he then looked at the flow patterns and looked at the mixing efficiency, etc. There are 2 or 3 papers that we have published so far on this design itself. So that's the power of these computational tools. But there is a level of risk in using these models because the models have a lot of uncertainties. Remember, all models are wrong, some models are useful. So if you're designing single-phase laminar flow, there is no uncertainty. There is very low risk. You can design these just in the computer and scale it up without any problem. If you go to turbulent flow, we are also in a good shape. Even though turbulent flow is complicated, we have built sufficiently robust turbulence models. But when you go for reacting flows, that in a turbulent medium, particularly the intrinsic kinetics that we measure under lab conditions don't remain invariant as you have a high level of turbulence, etc. And so the risk goes up, the uncertainty goes up. But when you go for multi-phase and multi-physics systems, the risk even goes higher. So if we are cognizant of this over a period of 10, 20 years, we can successively, continuously improve. But that rate may be accelerated because if we can merge the machine learning models with these complex physics, we can probably do much better in terms of increasing the robustness of these models. The reason for that optimism is what we see with large language models, and particularly in science. The Nobel Prize that was given this year is for Dennis Hassabis from Google, and both in physics and chemistry. They are for AI-based discoveries. Okay, so I've talked about 3 examples, but we have looked at a number of examples over the last 15 years or so. And anybody is interested, you're welcome to talk to me. And these are all the students that have contributed to this work. So with that, I will stop and open up the floor for question and discussion by my colleagues if I'm not able to join you in person.